All right, welcome back to part 3 of problem 3. In this part, we need to find the amplitude and the phase of motion. So we're going to do that by first analyzing what it gives us. So we have the equation for theta in respect to time here, which is amplitude times cosine of the angular frequency times time, plus the phase of motion, which is represented as phi. And then it also gives us the value for angular speed at time equals 0 here, which is 2.74 rads. And this little symbol here, you might not be familiar with this. So in this problem, we are using the lowercase omega as the angular frequency. But normally, in the past, we've been using the lowercase omega as angular speed, but we can't have, obviously, one variable representing two different values. So in this case, angular frequency is going to be the lowercase omega, and the uppercase omega here is going to represent angular speed or angular velocity. So let's start with writing some stuff out. So we know that theta of time here is equal to the equation, and we also know that when time is equal to 0, that is going to be equal to 0.0872 rads. So let's write that out. 0.0872 is equal to the amplitude times cosine, and time is equal to 0, so the angular frequency is also going to be 0, because a value times 0 is going to be 0. So that leaves us with cosine of phi. Now, it doesn't give us an equation for the angular speed. However, we know that the derivative of the angle is equal to the angular velocity right here. So if we get the derivative of this, that will be equal to this when time is equal to 0. So let's go ahead and do that. We know this value here. We're going to say theta time is equal to a cosine of the angular frequency times time plus phi. All right, and we're going to get the derivative of this, which will be omega. All right, so we have omega here of time is equal to the amplitude times sine of the angular frequency times time plus phi, which is, again, the phase of motion. And then we have to do chain rule, obviously, because we're doing derivatives. So this little omega here is going to come out, and that gives us our equation for the angular speed or angular velocity. Let's draw a little line here. So let's go ahead and simplify this, and let's try and get it to look somewhat similar to this, and I'll show you why we do that here in a second. So we know that 2.74, that the angular speed when time is equal to 0 is 2.74 rads a second. Then we have, we're going to move the negative sign over here, and we will move the omega over as well to simplify things. So we have the amplitude there times omega times sine, and this also is when time is equal to 0, so this will be 0 as well, which means we just have sine of phi right there. And so now from part 1, we did find out what omega was, because this is all obviously one problem. We're just solving multiple parts. So the angular frequency, or lowercase omega, we found was equal to 63.08. So now, if we plug that value into here and move it over and divide it, we're going to have a very similar equations, which will be very important. So let's go ahead and move that over. So we have 2.74 divided by 63.08. That is going to give us that value there. So 0.0434, we'll do 4 decimal places, very similar to that, is equal to the negative of the amplitude times sine of phi. All right, so now because this is a simple harmonic motion, we can actually divide these values out, and that will help us cancel out the A, the amplitude, and leave one variable phi, and then we can manipulate it to find that value. So we'll do that right over here. Let's isolate this, and we will go ahead and say 0.087, or actually, so here, we're gonna put the angular velocity on top, and you'll see why in a second. 0.0434 divided by 0.0872, and that is equal to, we'll also move, so okay, so negative amplitude sine phi and amplitude cosine phi. Okay, so this is pretty obvious. You're just going to divide that. So we'll do that here. 0.0434 divided by 0.0872. Okay, that's going to give us that value right there. So we're going to do 0.4977 is equal to, now here the amplitudes are going to cancel out, this negative sign is going to come down, and if you remember from trigonometry, this is very important if you don't know this, sine over cosine is equal to tangent, right? So we do sine cosine equal to tangent. That's a very standard trigonomic identity. You should definitely know that. If you don't, you're going to want to memorize that. So this becomes tangent of phi. Okay. So now here we've got a little bit of a problem because we have the phi in the tangent. You might be wondering, well, how the heck do we figure that out? How do we pull that phi out? Well, that's another piece of little trigonomic knowledge that you should know. If you have a constant equal to, let's say, sine, this works for tangent or cosine as well, and we'll say phi, but it also works for theta. This is also equal to phi arc sine, or sine inverse of the constant, right? And so you can quite literally pull this out. And this is the same as arc sine. So some teachers have you do sine inverse, some have you do arc sine. They're the same thing. There's no difference. For my case, I'm going to go ahead and keep doing sine inverse because that's how I learned it. But if you were to sub all of this for arc, same thing. So we're going to also move this negative over, right? So this is going to move over, and then we're going to swap the places. So that becomes phi is equal to tangent inverse of negative 0.4977. All right. Now make sure you're solving this in radians, okay? If you were to have your calculator in degrees, that would also be accurate. You would actually get the same answer if you were to set this to either degrees or radians. However, to do this correctly, you want to do radians, because if this were to give us a value that wasn't 0 and the angular frequency didn't cancel out, the angular frequency is in rads. So if you were to solve for phi in degrees and plug that in with rads, that's not going to work. You're going to get all kinds of errors. So you need to be consistent, right? consistency is key in mathematics. So make sure this is in radians. So we'll go ahead and check my calculator here. We are in fact in radians, so we're good to go. So we're gonna do tangent inverse negative 0.4977. All right, and that gives us our phi value here. So negative 0.46 rads, all right? So now we have phi. And if you'll notice, going back to this original equation here, we know what theta is at 0, right? So we know the answer to this equation. We know this is 0. This cancels this out, so we don't need to worry about that. We know what phi is now. That leaves one variable, so we can very simply find the amplitude simply by plugging everything in. So we're going to take 0.0872, because that's what this equals at 0 time. So that's equal to amplitude times cosine. This cancels out because it's 0 times 0. So that leaves our phi there. So that's negative 0.46. Okay. And we're going to then divide this value over, and that will give us our amplitude. So 0.0872 divided by cosine of negative 0.46. And that gives us our amplitude right here of, actually, here, we gotta move this down. That's not actually equal. Amplitude equals 0.0968. And that right there is our values for the phase of motion and the amplitude. So in the next video, we will be solving the maximum angular momentum of the bar. Thanks for watching.